The trachea is basically a tube that connects the throat to the lungs. You can have a scenario where a portion of the trachea needs to be removed. And when we remove a portion of the windpipe, well, usually we have to put the two ends back together. But sometimes we don't have enough length left, and we can't put the two ends back together. And for those patients, they're left with no option, and some of them die.
When we got together for the first time, one of the concepts was the idea of 3D bioprinting for tracheal reconstruction.
So the trachea has unique mechanical properties, and if we can replicate those properties using 3D printing technology and create a living graft using tissue engineering, we could hopefully produce a tracheal replacement, a living biological tracheal replacement.
So they walked across the street to the orthopedics lab where I work because we do cartilage research. And they came and said, hey, this is what we are seeing. We don't have a treatment. We're thinking, what can you guys do? And we're like, oh, we can do that now. We can work on 3D printing tracheas and segments and move forward from there. And they were shocked that this is technology that we have and exists and we can use.
Todd actually said, I think I can actually modify a two-head system and make it a bioprinter, and it worked.
Well, this is the MakerBot's Replicator 2X, and we've modified all of the extruder heads to be able to accept PLA and also to be able to accept a syringe filled up with living cells and what we call bioink. So in the bioink is collagen, food for the cells, and all this type of media, and our chondrocytes, which are the cartilage-making cells. A lot of this is the universal paste extruder, which you can go on Thingiverse and download. So the way it works is it'll put down a couple layer of PLAs, which are the structure, the scaffolding. It'll then inject the cells into the void space that it created. And when we remove it, then you have no more void spaces. You have the PLA and the gel, making it one solid unit. And we work with the physicians who they come in and they say, okay, this doesn't feel right, change this. They go, oh, this doesn't look right, change that. So we have open communication between us and the physicians. It's real nice for them to be able to hold something physically in their hand as we go through different types of versions and iterations.
The ability to prototype, examine, touch, feel, and then redesign within minutes, within hours, having multiple sets of prototypes to evaluate their physical and mechanical properties allows for the creation of this type of technology.
I must have made upwards of 100 different variations. Without the 3D printers to do this, the amount of capital we would need would be exponential.
MakerBot hardware and software has been instrumental in allowing us to do this research. Without the ability to fabricate designs quickly, we wouldn't be able to do any of this.
The implications of our work can show that not only patients, young patients, pediatric patients that suffer from this, and there's a number in the hundreds of thousands of individuals in this country alone that suffer from this, can breathe with customized implants that we can design for them.
Knowing that I could potentially have designed something that'll end up saving someone's child is the most exciting thing I could ever ask for.
You are making a contribution to science, and you are helping patients in the long run. So it's something we do. It's a calling kind of for us.